So this question says list the transformations of the function shown. Now that's the parent function of a 1 over x function. So it's a over k times x minus d plus c. That's what the variables are that we're going to look at as far as transformations. As I already noted, this is the 1 over x function, otherwise known as the reciprocal function. So y equals 1 over x. And so let's look at what the a value is and what it's going to do to the function. The a value is 3, which means it's going to do a vertical stretch by a factor of 3. We're going to multiply the y values by 3. It's literally that simple. Don't change the x values, but multiply the y values by 3. The k value is negative a half. And what that's going to do is it's going to do a horizontal stretch because the ratio we're looking at is always the reciprocal of the k value. So the reciprocal of 1 over 2 is 2. So that's a horizontal stretch by a factor of 2. But the negative means that it's going to be flipped or reflected over the y-axis, right? The k value reflects or flips over the y-axis, the vertical axis. So it goes side to side. Last but not least, we have the d and the c values. The d value, because the general form is x minus d, is positive 4, which means it's going to shift 4 units to the right. And then the c value is going to be 6, which means it's going to shift 6 units up. And those are all your transformations that we would apply to that reciprocal function. So now we go ahead and move to the graph. If we go to graph this, we're going to start by graphing the reciprocal function. And the key points we want to do is 1, 1, 2, 1 half, and 1 half, 2. And then we draw our curve through those 3 points. And then we do the same thing in quadrant 3, but now with the x values and y values being negative. And we're going to draw a curve through those 3 key points. That is the function y equals 1 over x. Now we're going to apply the a value of 3, which means we're going to multiply the y values by 3. So looking at the first key point there, where I'm at a y value of 2, multiply 2 by 3, we get 6. Notice the x value still is 1 half. We look at the next key point, 1 times 3 is 3, x value is still 1. The y value, 1 half, goes to 3 over 2, x value is still 2 there. And so now we draw our curve through those 3 points, and that's half of the new transformed function. We do the same thing down in the quadrant 3, and so negative 1 half becomes negative 3 over 2, negative 1 becomes negative 3, and then the y value of negative 2 becomes negative 6. All the x values staying the same. And so we now draw our curve through those 3 points, and that is the fully transformed graph of y equals 3 over x. Now we go ahead and look at the k value. So because we want to horizontally stretch it by a factor of 2 and flip it over the y-axis, it's really just multiplying all the x values by negative 2. The first point we're going to look at here is the point 2 and 1.5. And so the 2 is the x value. We multiply that by 2, we get 4, and then we flip it over the y-axis to get negative 4. We do the same thing with every subsequent point along the curve, doubling the x value and then flipping it over the y-axis, and we get it to move to quadrant 2 from quadrant 1. And so there is our half of the transform function. And now we do the same thing in the bottom left quadrant. So we're doubling all the x values without changing the y values and then flipping them over the y-axis. And so you can see that that first point becomes 4, negative 1.5. Next point becomes 2, negative 3. And the final point there becomes 1, negative 6. And so we draw our curve through those 3 points, and that is the other side of the hyperbola, the other side of the reciprocal function. And so this is with the a and the k value applied. So this is 3 over negative 1 half x. Finally, what we're going to do is we're going to transform it with the d and the c values together. Now, a really key thing to notice here is that the original asymptotes that we had on the green function drawn there is we had one at x equals 0 and we had another asymptote at y equals 0 on the actual x and y axes. And so what the shift left and right are going to do is it's going to move the asymptote. So the asymptote is going to shift 4 to the right, which means it's going to be at x equals 4. And then the other asymptote is going to shift up 6. So that means the asymptote is going to be at y equals 6. So while that principle of shifting all the red points right 4 and up 6 still applies, we can actually instead look at how far they are from the original asymptotes. It's over 2 and down 3 to one of those points. And so I can move that point over 2 and down through 3 from where those asymptotes now meet. And so I'm going to do that same thing with another point. I'm going to go over 4 and down 1.5 from where the asymptotes meet. And then that last point that was -1, -6, that's going to be 1 over and down 6 from where the asymptotes meet. And so I'm going to do that same pattern to plot that point as well. And so now I have 3 points. That's half the hyperbola now drawn. And so I have that half in quadrant number 2. Now, as we go into the next quadrant for the other half of the hyperbola, we do the same pattern. We look at how far I was from where the asymptotes met, going over and up or up and over. It doesn't matter how you look at that, just so long as you keep that pattern consistent. So here I'm going up and then over, using that same pattern, same distance with both the x and y from the point at which those two asymptotes meet. Notice that last point doesn't fit when I transform that, so I've just drawn it with those 2 points. Altogether, this is the curve y equals 3 over -1/2 x minus 4 plus 6. And that is your fully transformed function. Last but not least, let's look at the domain and range. The domain here is x is a set of all real numbers, but then it has this restriction at the asymptote. X cannot be 4. The range is y is a set of all real numbers, such that y cannot be 6, because it has the restriction at that asymptote. But otherwise, it's every other x and y value. And so those correspond really nicely to the d and c values, but they don't do that always for all the parent functions, but they do for this particular parent function.